Oh, that doesn't work. I got to turn the machine like that. Okay, so I was going to start 5.1. I realize you still may have some questions from 4.9. So I'll lecture on 5.1 for a while. I was hoping to give you some time for questions and answers from 4.9. So if there's anything else in 4.9 you want to look over, then I might give you some time later on for that. But I'm going to get started at least with 5.1. Okay, so time-wise, we're fine. We only have the one last chapter and aiming for now, Thursday, December the 10th for the last regular exam. Mind you, our final exam is Wednesday, December 16th. That's less than a month now, from 11:10 to 1:40. Okay, and you say, how do I study for the final? Just study the old exams. Okay, the old exams. I'll draw questions from the old exams as a template for the final exam. Okay, so let me get started with 5.1. It may be a while until I actually do any homework problems in 5.1 because there's a lot of theory behind what I have to go over. So let me get started with that. Okay. So chapter 5, the topic is integrals. No big surprise, I introduced that 4.9. Now, 5.1, however, is going to seem at the beginning to have no relation to 4.9. Okay? They're going to seem totally different, but hang in there. By the time we're finished with the chapter, everything will be brought together. Okay, so 5.1, page 266. We're trying to find the area under a curve of this function. Okay? Let's assume it's a positive function. It doesn't have to be positive. Let's say it's positive. Okay? I'm bounded by x equals a, x equals b. S is the surface that I'm interested in. I want to find the area of this. And of course, offhand, it looks like there's no good way to do it unless I have a nice shape. Right? Now we know how to find the area of that. We know how to find the area of that. This one you can break up into a whole bunch of triangles and say, just add up all the areas, right? Okay. But what do I do if I have a curve like this one? Okay. So here's y equals x squared. From 0 to 1 is the 0.11. So how can I find the area under the curve here, right? So we're not even going to answer the question right now. We're just going to approximate it. Okay, suppose I take the interval between 0 and 1 and chop it up into so many pieces. In this case, 4 equal pieces, S1, S2, S3, S4. Okay, so they went 1/4, 1/2, 3/4, 1. Okay, so I have 4 smaller pieces. So we're claiming if I take this area plus this area plus this area plus this area, I get the whole area, right? Now, of course, your first impression is, well, that doesn't really help because I still don't know how to find the area of something like that. Okay? So what are we doing? What's this picture about? In some sense, we're cheating. Okay? We are replacing the areas with rectangles. Why do I want rectangles? I know how to find the area of a rectangle, base times height, right? So notice they drew 4 rectangles, and each rectangle is too big, right? The only area I really want is under the curve, right? It's this picture here. I'm replacing it with this rectangle, this rectangle, this rectangle, this rectangle. It'll clearly be too much. Okay? So if I sum the areas of these 4 rectangles, which I know how to do, it's just base times height, base times height, base times height, base times height, add it up. I will definitely have an overestimate. Is that right? Because I got extra area. But you can tell what the extra area is, right? I picked up this part which shouldn't be there, and this is extra, and this is extra, and this is extra. Okay? So I can add up these 1, 2, 3, 4 areas. It'll be an overestimate. Is that right? Now, look at this picture. Underestimate. Right? They again picked rectangles. Okay. That first height you can't see is because the first height is 0. So the first rectangle has an area of 0. Okay, then this one, this one, this one. This is definitely an underestimate because I'm really trying to find the area under the curve. I'm replacing it with 4 rectangles. In fact, the first one's not even a rectangle. It has no height at all. But it's definitely too small. That's too small. That's too small. That's too small. So look at the area that I'm throwing out, right? All the white space, that white space, that white space, that white space, that white space got left out. So that would give me an underestimate. But at least I can now say the true area is something between this one and this one. Does that make sense? Okay, so what did they do here? It looks like they took the function values at the right endpoints. Okay, the height is the function value at 1/4, 1/2, 3/4, and 1. And then they had a delta x. In this case, the delta x's are all 1/4. Okay. What did they do over here? They took the function value at the left endpoint. So the left endpoint was 0. If you plug in 0, you get 0. Okay. This height is f of 1/4. This height is f of 1/2. This height is f of 3/4. They took all the left endpoints, figured out the height. The bases are the same. The bases are all 0.25 or 1/4. And just add them all up. Base times height, base times height, base times height, and so on. Okay. Now, the area of these 4 rectangles added together comes out to be this. So that means I know the true area is less than 0.46875. Okay? They figured out these 4 areas. You will learn how to do this too. It's actually not that hard. It's basically just base times height. Okay, now, they added up these 4 rectangles, although the first rectangle has a height of 0. Okay? You add these up, 0.21875. Definitely too small. So I can say the true area under the curve is between the two numbers, 0.21875 and 0.46875. Okay. So they chopped this region up into 4 pieces. Rectangles are too big. Rectangles are too small. Okay. Now what are they doing in figure 6? Same thing with 8 rectangles. Left endpoints, right endpoints. Okay. So chop it up in 8 pieces. Take a look at this compared to this. This one's better. It's still an underestimate, but it's better. And take a look at this compared to this. This one's better. Still an overestimate, but I got better. They added all this up, they added this up. The sum of all of these rectangles area is 0.27 blah, blah, blah. The sum of all these is 0.398 blah, 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 blah. So I can say the true area is between these two numbers. That's much better, right? I mean, it's still off. It's still off by about 0.12 or something like that. So that's better than this. We're off by, what, 0.25. Okay. Look at this. This time they chop it into more pieces. I can't tell how many pieces there are, but it's better. Okay, I'm on page 368, 369. You don't really have to write anything down, just concept here. N equals 10. Okay, what is 10? N is the number of pieces you're chopping up the region into. Okay, so chop, chop, chop into 10 pieces. So if you're going from 0 to 1, each of these is 1/10 or 0.1. R means the rectangles are formed by picking the right endpoint. So that one, that one, that one, that one, that one, that one, that one. Okay. L stands for using the left endpoint. So chop it up into 10 pieces. This is now 30 pieces. This is 50 pieces. Take a look. 50 pieces looks much, much better compared to these, right? So it looks like the greater the n, the greater the approximation. Nevertheless, each of these is too big, right? That sum is too big, that sum is too big, that sum is too big, but this looks more and more like what you're aiming for. But they're all overestimates. Now look at the underestimates. N is 10, 30, 50. Okay. Again, the approximation gets better and better and better. You're looking at the lost area is the white space, right? So look at how much white space there is here. Much less white space. Here, it's very hard to even tell the white space, right? So the approximation gets better and better and better as n gets bigger and bigger. Okay, so L stands for using left endpoints. R stands for using right endpoints. And the little subscript like R30 or L50, the 50 or the 30 tells me I'm chopping up into that many pieces. Okay. So we would expect these two numbers to be even better approximation. R50, 0.3434, L50, 0.3234, much closer. Okay, now, they did this on a computer, obviously. You don't want to do this by hand. Now, the stuff we're going to do by hand, we'll chop it up into, I don't know, 5 pieces, 8 pieces, something like that. We're not going to do 50, then you program a computer to do that. Little mini table here on page 367. They did the left sums, all of which are too small. You can tell they're all too small. They did the right sums, all of which were too big. Here's the table. And it's 10, 20, 30, 50, 1,000. You see what's happening? The approximation gets better and better and better. I mean, look at the picture here. Even for n equals 50, right? This looks pretty good. This already looks pretty good. Okay. So you can see what's happening. N is 30.316, 0.35. But as you go farther down the table, both the left sums and the right sums become closer and closer to the true value. Let's look at 1,000, 0.3328, 0.333, right? It looks to me like the true value is about 0.333, more commonly known as 1/3, right? Maybe the value converges to 1/3. And of course, if you want better approximation, let n get bigger. N could actually approach infinity using limit language. Suppose it was 1,000, a million, a billion. Okay, you'll see it get really close to 0.33333, and so on. Okay. So that is that picture. Next picture I want to show you. Way over on page 373. E to the negative x. Okay, they chopped it up into 1, 2, 3, 4 pieces. So if I'm going from 0 to 2, 2 divided by 4 is 1/2. So that's 0.5, 1, 1.5, 2. Okay. We've discussed left endpoints and right endpoints. Look at what's happening here. It looks like they're not taking the left endpoint or the right endpoint for each rectangle. They're picking the midpoint. Midpoint. So they go halfway, go straight up, draw that rectangle. Same thing here. Go halfway between 0.5 and 1, 0.75. Go up until you touch the graph, draw a rectangle. Same thing here, same thing here. You see what's happening? This is the true, this is the true area that I want for the first region. Okay, I'm tracing it there, right? They're replacing with this. That looks like a pretty good replacement because I lost this area here, right? I lost this, but I gained this. Is it an exact cancellation? Probably not. Maybe it is, maybe it isn't. We don't know. And so when I use the midpoint, it looks like right off the bat, it's a pretty good estimate, although I won't be able to tell, is it an underestimate or an overestimate, okay? So quite often when you do the left endpoints and right endpoints, like we were doing back here, right, you can tell right away, oh yeah, overestimates, these are too big. Underestimates, these are too small, right? But when I pick the point right in the middle, the midpoint, and I'm on page 373, the approximation looks pretty good, right? Although I can't tell if it's an upper estimate or a lower estimate. Okay. So that's what's happening right here. All right, so what are we doing? We're trying to find area under a curve like that, or they'll give us functions later. So we're kind of not even answering the question. We're delaying the question. We're cheating. We're replacing with rectangles. So we're only going to be able to come up with estimates right now. Okay, so let me try to get started with something. So 1, 2, 3, 5, 7, 13, 15, 17. Let me start you off with number 2. And it's going to be a little bit awkward because I have to show you the book and at the same time write stuff. So I have to keep bouncing back and forth between the two. Okay, number 2. Okay. Here's the graph. I'm trying to estimate the area under the curve from 0 to 12. So let me trace out the area that we want. That curve down here, come straight down and back over. Okay, one more time. The area under the curve. Go straight up, curve down there, down and over. Okay. Use 6 rectangles to find estimates of each type for the area under the given graph from x equals 0 to x equals 12. Okay, so chop it up into 6 pieces. So that means my delta x is 2. Okay, so 2, 4, 6, 8, 10, 12. Okay. So if I were to trace the regions, there's the first region between 0 and 2, and then between 2 and 4, like that, and between 4 and 6, and likewise 6 and 8, 8 and 10, 10 and 12. Okay. I'm going to cheat. I'm going to replace them with rectangles. You say, well, that's not going to be accurate. Yeah, we know. It's not supposed to be accurate. We're only going to give estimates. All right, so please notice the notation. L6, R6, M6. 6 is the N. I'm chopping this region into 6 pieces, which means delta x is 2. L means I'm using the left endpoints. R means I'm using the right endpoints. M means I'm using the midpoints. Okay. So this is going to be a little bit clumsy. Try to write back and forth here. Okay, so I'm going to say delta x is 2. Okay. 12 divided by 6. All right. 12. Chop it up into 6 pieces. Okay. So between 0 and 2, 2 to 4, 4 to 6, 6 to 8, 8 to 10, 10 to 12. Okay. So I have 6 sub-intervals. 6 sub-intervals. See, what is a sub-interval? It's a smaller interval. Okay. The whole interval was from 0 to 12, right? Including 0 to 2. Okay. So here are the 6 sub-intervals. 0 to 2, 2 to 4, 4 to 6, 6 to 8, 8 to 10, 10 to 12. And yes, this is very tedious. In case you're wondering, in general, you don't have to write all these down. For this first problem, I'm going to write them all down. But in general, you know what to do once you get it, I suppose. Okay. So there are 6 smaller intervals, right? 0 to 2, 2 to 4, 4 to 6, 6 to 8, 8 to 10, 10 to 12. left, right, middle. Okay. So L is for left, R is for right, M is for middle. Maybe I'll write it down here. Left endpoint, right endpoint, midpoint, midpoint. Okay, so just for this first exercise, in general, we're not going to write all this down. Just the first time I'm going to do it. Okay, so let's put down the left endpoint on each subinterval. So from 0 to 2, what's the left endpoint? 0. Between 2 and 4, what's the left endpoint? 2. Between 4 and 6, what's the left endpoint? 4 and 6 and 8 and 10. That's easy, right? Left endpoint. Now, same thing on each interval, give me the right endpoint. So on 0, 2, what's the right endpoint? 2. For the interval from 2 to 4, what's the right endpoint? 4 and 6 and 8 and 10 and 12. Is that right? That's not too hard. And likewise, on each subinterval, give me the midpoint, the one right in the middle. So 0, 2, what's the midpoint? 1. And 2, 4, what's the midpoint? 3. 4, 6, what's the midpoint? 5 and 7 and 9 and 11. Right? So that should not be that bad at all. You guys okay with that? Now, what do I do with all these guys? Okay. My representative rectangle that I'm going to pick is going to be the height at these corresponding x values. Okay. So I'm going to do base times height, 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 base times height. Actually, all the bases are the same, 2. Right? I mean, this base is going to be 2. They're all 2. Okay. So if I may illustrate, the first rectangle is going to go from 0 to 2. So the base is 2. And the next one's from 2 to 4. And then 4 to 6, 6 to 8, 8 to 10. Okay, so they all got the same basis. The question is, what's the height going to be? The height's going to be depending on whether I pick the left endpoint, right endpoint, or midpoint. Right? So if I pick the left endpoint, the first one, I take 0. Okay? So I would go straight up until I touch the graph and imagine drawing a rectangle right here. Okay? And I don't really want to do it because I'll be writing in my book, but that would be the first rectangle. Looks like it's too big. And then from 2 to 4, the left endpoint is 2. I'll be going like that. And that would be too big. Same thing from 4 to 6, I'd be going there, and that would be too big, and so on. Okay? So essentially, I'm picking all the left endpoints. So here we go. I'm trying to write this down now. And I can't show you this at the same time, but I'll give it a try. Okay, so for 2i, L6. Okay, so it's base times height, 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 base times height. Okay, but all the bases are the same, the 2. Okay, so I should write it like this. L6. Okay, so L6 is equal to 2 times f of 0, 2 times f of 2, 2 times f of 4, 2 times f of 6, 2 times f of 8, 2 times f of 10. Okay. Base times height, base times height. These are all 2s. Base times height, base times height, base times height, base times height. But it's easier just to factor out all the 2s. Okay. So normally we just factor out the delta x. And just put f of 0, f of 2, f of 4, f of 6, f of 8, f of 10. The 6 height. F of 0 means the height at 0. There. F of 2, the height at 2. So here's the second rectangle between 2 and 4. So watch, I go here, go straight across and down. It's too big. Okay. Here's the last rectangle. It's going from 10 to 12. If I take the left endpoint, I want the height at 10. So here's 10. So watch what I'm doing. Go straight up, draw this rectangle. Again, that's too big. So all of these rectangles are going to be too big. Okay. Now, I just need all these heights. So I just read it off the graph, and we'll just guesstimate now. Okay. At all the left endpoints, 0, 2, 4, 6, 8, 10. Okay. So I want those 6 heights. Just read it off the graph. So f of 0 looks like it's 9. I know it's a little bit clumsy because I have to write and then take away this book, but that's the way we are here. Okay, what's the height at 2? Well, 8.8 maybe. Just guesstimating here. The height at 4. Okay, it's a little bit more than 8. I'm going to say 8.2. F of 6. Let's see. That's 5, 6, 7. So a little bit more than 7. Not quite half. I'll say 7.3. F of 8. Looks like it lands right on 6, right? 6. And finally, f of 10. 4. Okay. And just punch it in the calculator. If I can do that quickly. Can't hold the paper there. Okay, let me add these up. 9 plus 8.8 plus 8.2 plus 7.3 plus 86.6. And we know it's an overestimate. The text asks, is it an under or overestimate? It's an overestimate. Okay, because these rectangles are all going to be too big. Right. Do the same thing for R6. We know the bases are all 2. Now I take the function value at all the right endpoints. So the function values are going to be at 2, 4, 6, 8, 10, and 12. But if you stop and think about it, we already did the heights at 2, 4, 6, 8, and 10. That's just a copy. The only new one is the function value at 12. Right? So I'm not going to write all this. It's base times height, but all the bases are the same. There's still 2. So again, factor out the 2. Oops, I didn't want to. And now the function value at the right endpoints, 2, 4, 6, 8, 10, and 12. So f of 2, f of 4, f of 6, f of 8, f of 10, f of 12. Okay. But 5 out of the 6 I already got. So why don't I just peek over and copy 8.8, 8.2, 7.3, 6, and 4, right? That's the same as that. 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 Right? So the only new one is f of 12. 1. And there we go. Okay, so let me see. 70.6. And I'm going to, this is an underestimate. It's an underestimate, okay, because between 0 and 2, if I take the right endpoint, which is 2, right? So here's that particular rectangle. So watch how I'm tracing it. Go straight up until you touch the graph, draw a rectangle. So that's too small. Same thing between 2 and 4. Use the right endpoint, 4, go straight up, draw a rectangle. So I'm losing some space. The very last one, between 10 and 12, if I pick the right endpoint, I would choose 12. So I go straight up to there, and this is my rectangle, and I'm losing all of this area right here. Right? It's supposed to be like this. I'm only getting this. So that's an underestimate. All right, and can you guess what do I do for the midpoints? Okay. I'll take the function values, the heights, at 1, 3, 5, 7, 9, 11. Okay. So I need the function value at 1. So here's the first rectangle. I'm supposed to go from 0 to 2. I would go straight up, touch the curve, and go like that, and use that rectangle. So it's pretty good, right? Let me show you the last one. Between 10 and 12, what's the midpoint between 10 and 12? 11. So the height would be like so. I would draw this rectangle. So you can see I gained extra piece here, but I lost all of this here. Okay. Does it exactly cancel out? Probably not, but that's the best we can do. So now I want the function values at all the midpoints. So it's still base times height and so on, but all the bases are still 2. So factor all it's going to be 2 times something, 2 times something, 2 times something. Why don't we just factor all the 2's out? And then I want the function value at all the midpoints. F of 1, F of 3, F of 5, F of 7, F of 9, F of 11. Those are the 6 midpoints. So that's where you would start to quote unquote draw the rectangle. So let's say F of 7, you're going between 6 and 8. You go straight up until you touch the curve. That's the function value at 7. And then you draw this rectangle and cut across here. Okay. So again, you gain something on this side, but you lost something on the other side. So might be a good cancellation. Okay, so now I got to get the heights again. So F of 1. Okay, a little bit under 9. How about 8.9? F of 3. Here's 3. So a little bit more than halfway. I'll say 8.6. F of 5. And here's 5. Go like that. So a little bit lower than 8. So I'll say 7.9. Just eyeballing it. F of 7. Here. So where's here? 4, 5, 6. Between 6 and 7, more than halfway. So I'll say 6.7 maybe. F of 9. Here's 8, so here's 9. It looks like it lands right on 5. And finally, F of 11. Here's 11. Okay, it's a little bit lower than 3. I'm going to say 2.9. Okay. And I punch this out. And I'm going to go with this is the best estimate, right? I don't know if it's an under or an overestimate, but it's the best estimate, period, because it sort of accounts for the cancellation, right? For the other rectangles, you know for sure it's either too big or too small. Here, it's a pretty good estimate, but I don't know if it's too big or too small. Okay, so let me print this out very quickly. 2 times 8.9 plus 8.6 plus 7.9 plus 6.7 plus 5 plus 2.9, close parentheses, 80. Okay, so what I'm going to say, in this problem, I know for sure the area is between 70.6 and 86.6 because this is for sure an underestimate. This is an overestimate. So the true area lies between 70.6 and 86.6. And our best guess, our best estimate is 80 for now. Okay, so that's the idea behind the problem. And we've only done one problem for today. It took a long time to develop it, but that's the concept. Okay, so from the picture, get rectangles using the left endpoint, right endpoint, or midpoint. And your question one, I'm sure is very similar. Okay, and you got the answer in the back of the book. Okay, all the other problems are hard. Okay. Now, I don't have time to do it now. I'll save this maybe for tomorrow. But what if they don't give me a picture? They give you a function. Well, this is actually easier. In fact, it's more accurate because here I'm just eyeballing it, right? Oh, where is this? Is it 4.2 or 2.9, right? Okay. But here you get more accuracy because you just plug right into the function. There's no guesswork. You're not off by a little bit. You'll be able to get it pretty much exactly. Okay. I'll show you something like that. I was going to start that tomorrow, but it depends. I was going to look at see if anybody has any questions from 4.9 for now. So we only have about 10 minutes left. Okay, so that's formally all I had for now. Let me stop the share, see any questions in the chat. Okay, so 4.9, it looks like 21, 33, and 37 were asked for. Okay. So let me write this down. 4.9, 21, 33, 37. We have about 10 minutes. Okay. So we'll give that a shot. Okay, so that's the basic idea for 5.1. I know I only did one problem, but it took me a while to develop it. And hopefully tomorrow we'll go farther. Okay, so let me go back and share the screen. Yeah, we're still recording, so we're good. All right, so back to 4.9. .921. Whoops. 4.921. F of x is equal to 2x to the fourth plus 4x cubed minus x all over x cubed. X is greater than 0. Find the most general antiderivative. Okay, it basically means integrate this thing. We don't really use this stuff, I think. Okay, so we're gonna, there is no quotient root for integrals, so we just divide it. That divided by that is 2x. That divided by that is just 4. That divided by that is negative 1 over x squared. Right? All right, so find the most general antiderivative. So I want the integral of 2x plus 4 minus x to the negative 2 dx. So power root, 2x squared over 2. Integral of a constant is constant times x, or x, minus power root, x at -1 over -1, plus a constant. Clean it up, cancel, cancel. X squared plus 4x, double negative, so positive 1 over x plus c. So that looks like that's my answer. Okay. And see 33. Let's ask for f prime of t equals 4 over 1 plus t squared. F of 1 equals 0. Okay. This information tells me my answer isn't going to be blah, blah, blah plus c. I'm going to be able to figure out the c. Okay. So instead of infinitely many functions, different by constant, it's just going to be one function. Okay. So notice this is backwards than what we've been doing all semester. All right, all semester, here's a function, find the derivative. Now we're going backwards. Here's the derivative. What was the original function? All right, integral of 4 over 1 plus t squared dt. Think of it as 4 times 1 over 1 plus t squared. Okay, 1 over 1 plus t squared. What function has a derivative of 1 over 1 plus t squared or 1 over 1 plus x squared? That was your arctangent. Right? The derivative arctangent of t is 1 over 1 plus t squared. And think of it like that. Okay, now f of 1 equals 0 means I plug in 1 and the answer I get is 0. So 0 is the result of plugging in plus c. Inverse tangent of 1 is pi over 4. Because tangent of pi over 4 is 1. That means inverse tangent of 1 is pi over 4. You might recall in a unit circle, so this is scratch paper here. If you have a unit circle at pi over 4, 45 degrees, both x and y are radical 2 over 2, radical 2 over 2, radical 2 over 2. So if you take sine over cosine, it's radical 2 over 2 divided by radical 2 over 2, which is 1. So 0 is 4 times pi over 4 plus c. Cancel, cancel. 0 equals pi plus c. Subtract pi. So c is equal to negative pi. Okay, and just plug that back in. So instead of blah, blah, blah plus c, it's blah, blah, blah minus pi. So the function f of t, I can now write as 4 inverse tangent of t minus pi. So it's not infinitely many functions, it's only one function. Okay. This one function has two properties. Property number 1, the derivative is 4 over 1 plus t squared. The derivative is. Property number 2, when you plug in 1, you get 0. Plug in 1, 4 times pi over 4 is pi, pi minus pi is 0. Okay, so there it is.